Okay, so maybe we can start. Shashank. Sorry, is that?
I've started recording.
Yes, yeah. Shashank, right? Yeah.
Yeah.
Is it also live on YouTube?
I'm trying that, but that doesn't seem to be working.
Okay.
Uh,
Yeah. So maybe we can skip that.
yeah. Yeah.
Yeah. Okay. Okay. Yeah. Hello, everyone. Welcome to the session 9B of STOC 2020 on anything that randomness has to do with computing. In this session, we will learn about the state of the art in pseudo-random generators, extractors, random walks, and sampling algorithms. Our technical host for this session is Shashank Srivastava. Thank you, Shashank. Let me remind everyone of the format briefly. Each slot is 10 minutes, 5 minutes for the presentation and 5 minutes for the questions. The audience can ask questions either through Q&A or through the raise your hand feature. I will read out the questions asked through Q&A at the end of the presentation. And if someone raises their hand, we will unmute them and then they can ask their question. You can also ask your questions on the Slack channel for each paper. And also, after this session has ended, if people want to hang out with the speakers, they can use the raise your hand feature and we can then promote them to panelists. And maybe you can hang around for 20 minutes or so. Okay. So yeah, so let's start with the first talk. Liang, you can share your screen.
Okay.
Yes, okay, cool. Yeah, so our first speaker is Liang Tan, and he will tell us about fooling Gaussian PDFs via local hyperconcentration.
All right. Hey, thanks so much, Ankit. And thanks everyone for coming. I'm so happy to see so many familiar and friendly names. But anyway, this is Fooling Gaussian PDFs via local hyperconcentration. It's joint work with Ryan Donald at CMU and Rocco Savidio at Columbia. And please ask questions as I go along. Okay, so I'll only have time to state the result, so let me state the result. Good. So this is a talk about basic class of functions, polynomial threshold functions, or PTFs over Rn. So these are functions mapping Rn to plus minus 1. And they have the form f of x equals sine of p, where p is a polynomial. So it's a very natural class of functions. So let me give you an example. Here we have a polynomial p, a quadratic polynomial p, denoting an ellipsoid. And f is simply the function that takes value 1 within the ellipsoid and minus 1 outside the ellipsoid. And in this talk, please think of n as tending to infinity as usual, not 3. So for us, PTFs will be high-dimensional geometric objects, a natural representation of such objects. And for this reason, they are intensively studied both within theory and also beyond theory. Okay, so that's the class of functions. And there are many ways you can measure the complexity of a PTF. In this talk, we'll focus on one of them, a natural one, which is the degree of the polynomial p within the sign, which we'll call d for the next few slides. So here we see on the left, we have d equals 1, which is an extremely interesting class. It's a class of all half spaces. With d equals 2, we capture things like ellipsoids. And even here, we see that with 5 and 6, we're looking at some pretty complicated polynomials and functions. And in fact, in this talk, please think of d as growing with n, not 3, not 5, not 6, but from concreteness, we can think of d as, say, log n. So we're living in n-dimensional space, and we are looking at the sign of a polynomial where the polynomial has degree log n, let's say. Okay, good. There are many questions we can ask about PTFs. Many questions have been asked and have been studied. In this talk, we'll focus on just one of them, discrepancy sets for PTFs over Gaussian space. So let me try to state what this problem is. So we consider our ambient space Rn endowed with the standard Gaussian measure. We want the small set of points, the smaller the better, denoted here in purple, with the following very nice property. So this is the set of points, and we would like it to be the case that for every degree D PTF F, if F's Gaussian volume is delta, then we'll like it to be the case that F accepts roughly a delta fraction of my specially chosen points. So this is a small set of points that up to 0.01 error approximates the Gaussian volume of every degree D PTF. That's the problem. And if we think about it for a few minutes, we see that a random small set of points works great. So this is really a problem in explicit constructions. And as Ankit said, this is really a talk about pseudo-randomness and explicit constructions and de-randomization. We want an explicit small set of points. Okay, so let me restate the problem in terms of PRGs. PRGs are more well studied over Boolean space, but I think they're very natural over Gaussian space as well. So epsilon PRG for class C is an explicit function mapping R bits to Rn, such that for every function f in C, its expectation under the Gaussian measure, its Gaussian volume is roughly very well approximated by its expectation under the output of the generator. This is the standard definition of a generator. However, now we're looking at Rn. And we can study PRGs for all sorts of function classes. In this work, we study PRGs for degree D PTFs. And just to draw the connection between PRGs and discrepancy sets, if R denotes the seed length of the PRG, then it's easy to see that the range of a PRG is exactly a discrepancy set. So R and the size of the discrepancy set are exactly equivalent up to an exponential factor. Okay, with that, I can conclude my talk and state our result. Our main result is a new PRG for PTFs over Gaussian space. We give an epsilon PRG for degree D PTFs over Rn with seed length d to the log d times log n. So the main conceptual contribution of our work is to bring the previous 2 to the d dependence down to d to the log d. So this question has been quite well studied. Previous seed lengths has dependence at least exponential in d, and we achieve quasi-polynomial in d. We still have a long way to go. This is far from optimal. The probabilistic method shows that there exist PRGs with seed length linear in d. So a very nice next step would be to bring our seed length from quasi-poly in d down to poly in d, and hopefully one day even linear in d. Let me just conclude the talk by saying that the Gaussian space version of the problem that we study is in fact a special case of the Boolean space version of the problem, for which the current best seed length is still 2 to the d. We are hopeful that our techniques can lead to progress on this problem, but for now, our result is still specific to Gaussian space, and it'll be extremely interesting to make progress on the Boolean space version of the problem. Okay, thank you so much.
Thank you, Liang. So we have a question by Ishan Chattopadhyay. Is there hope of extending your techniques to get similar seed length in the Boolean domain?
Thanks for the question, Ishan. Absolutely. We believe that also the probabilistic method also gives like a linear and d seed length over Boolean space, and we very much would love. In fact, if I had more than 5 minutes, I'll tell you about some of the techniques that went into this work. But briefly, we believe that the main techniques that we develop in this work also apply to Boolean space. We are unable to prove it, but we believe that they remain true over Boolean space. So absolutely, we think that the same analog of the result holds over Boolean space. And not just that, we think that the same analogs of our lemmas and our results hold over Boolean space. We're just unable to prove it.
Thank you. The next question is by Jinho Lee. Is there any hope to improve the dependence on epsilon in the seed length?
Great question. Yes, there is hope. The probabilistic method shows that we can get log 1 over epsilon, and we are only getting 1 over epsilon to the log d. I would love to do it. Yeah, I'm thinking about it. Yeah, there's definitely hope. It will be very nice to get our sort of poly type dependence on 1 over epsilon down to logarithmic. Yes.
Thank you. Next question is by Madhur Tulsiani. can we get a similar result, maybe even for regular PTFs in the Boolean case?
Great question, Mother. Thank you. That would be very nice. And indeed, as Mother very nicely asked, this shows hope that we can prove the same result over Boolean space even for regular. But for various reasons, even for regular PTFs over Boolean space, we are unable to get this similar result. But certainly, as Mother said, the natural first place to start, I think, would be to start with regular PTFs over Boolean space, because there's a very nice connection between regular PTFs over Boolean space and PTFs over Gaussian space. But answer to Mother's question is, unfortunately, even for regular degree D PTFs over Boolean space, we cannot get an analog of our result yet.
Thank you. Next, Ishan says thanks. Next, we have a question by J. Morris Rojas. Is there any refinement for sparse polynomials of degree D?
Ooh. Great question. Over Gaussian space, I haven't thought too much about sparsity over Gaussian space because, yeah, Gaussian space is sort of rotationally invariant, but certainly over Boolean space, I think it's extremely natural, and it has been studied, just a class of sparse PTFs over Boolean space. So as I said in the second slide, degree is not the only way to parameterize the complexity of a PTF, of course. Sparsity is another very natural one and has been studied, and it's very natural to study sparse PTFs over Boolean space as well.
Thank you. Next question is by Salil Vadhan. Can you give a sentence or two teaser about the techniques?
Sure, absolutely. Thanks for the question. We proved what we call a local hyperconcentration theorem over Gaussian space. We can actually, another way to think about it is maybe like a random restriction lemma over Gaussian space, but for polynomials. So we are perhaps more used to thinking about random restrictions of circuits and random restrictions over Boolean space. But what we actually show is a random restriction random restriction lemma for polynomials and over Gaussian space. So very roughly speaking, if you take a polynomial living over Gaussian space, you hit it with a random restriction. It's fine if that's not 100% clear what that means. And if you hit a degree D polynomial over Gaussian space, it becomes morally degree 0, morally constant. So sort of, this is one of the reasons why I'm very excited about this work. It's a new random restriction lemma for polynomials over Gaussian space. And we hope, in fact, that the same random restriction lemma with the same parameters also hold over Boolean space, which I think would be very exciting if we can prove that.
Okay, thank you. Next, we have Ishan again, I guess, related to the point you just said. Is there a concrete, simple to state technical conjecture that would help extend to the Boolean case?
Absolutely, Ishan. It's in our paper, and I'm also happy to state it maybe somewhat informally here. So if you have a degree D polynomial over Boolean space, over bits now, n bits, a polynomial, not a PTF, a polynomial, if you hit it with a random restriction with star probability 1 over d to the log d, then P, the polynomial hit by that restriction, becomes morally constant. That's not well defined, but roughly speaking, a morally constant polynomial is one whose variance is a tiny fraction of its expectation. So even though syntactically it's a degree D polynomial, its variance is a tiny fraction of its expectation. So for all intents and purposes, it's morally a constant. So that's the hope for sort of random restriction or switching lemma for polynomials.
Thank you. Okay, thank you, Liang.
Thanks for the questions.
You can unshare a screen. Okay, Jesse.
All right, here we go.
Okay, cool. So yeah, the next talk is by Jesse Goodman, and he will tell us about extractors for adversarial sources.
Yeah, hi, I'm Jesse, and I'll be talking about constructing extractors for adversarial sources using extremal hypergraphs. And this is joint work with Ishan Chattopadhyay, Vipul Goyal, and Shinley. So randomness extractors are motivated by the question, how can we purify the imperfect randomness that we find in nature? And so formally, a randomness extractor is a single deterministic function defined with respect to some family of distributions, curly x, and it gives you the guarantee that given any random variable in this family as input, it outputs bits that are epsilon close to uniform. And the main question is, what's a reasonable choice for this family of distributions? And can we extract randomness from such a family? And so one kind of typical thing to do is as follows, is to assume you have some natural sources of randomness and that you can take some random samples from each natural source and concatenate them all together. And then it's typical to make two assumptions here. And the first assumption is that each sample that you took has some randomness in it. And furthermore, that all of the samples that you take are mutually independent. And this captures the classic independent source model, where the family of distributions is defined as follows. So each distribution in the family consists of big N independent sources, which are mutually independent, and each source in that product distribution is guaranteed to have min entropy at least K. And you can think of this as just kind of a measure of how much randomness is in the distribution. Bigger K means bigger randomness, means easier to extract uniform bits from. And so people have been very successful in constructing extractors in this setting, but kind of what we challenge in our paper is whether this is actually a reasonable selection for a family of distributions. And in particular, we might run into two problems with this model. So first of all, some natural sources of randomness might actually output samples that have no entropy at all. And so things like Zener diodes are known to do this. And second of all, some natural sources of randomness might actually be correlated. And so that kind of challenges this mutual independence condition here in the classical model. And so what we'd like to do is kind of generalize this classical model to something more robust and construct extractors for this more robust setting. So in order to do this, we kind of generalize the standard model in two ways. So first of all, we assume that some of the sources in our collection of independent sources might actually have no entropy at all, and we call these bad sources. And then we generalize it further by saying perhaps these bad sources can actually depend on the good sources in some bounded way. And so through these generalizations, we introduce the class of adversarial sources defined as follows. And so a distribution X is defined as an NK adversarial source of locality D if it consists of big N sources, each over bit strings of length little n, and two conditions hold. So the first condition is the guarantee that there are at least big K good sources somewhere in there. We don't know where they are. And each good source has min entropy at least K. And then the second condition is the remaining sources are bad. They may not have any entropy at all. And furthermore, they can depend on up to D of the good sources. And so our goal in this paper is to construct extractors for this new model of distribution. And so our results are exactly of this form. So we explicitly construct extractors for the class of adversarial sources, and all of our extractors will output many bits with exponentially small error. So here are kind of the parameters that we want to optimize for. And even though we introduced the class of adversarial sources, it turns out that some extractors constructed previously do in fact extract from some settings of adversarial sources. So in particular, in 2016, Shahadah and Lee constructed an extractor that can extract from two hidden good sources among an arbitrary number of bad sources. But those two good sources need to have pretty high entropy. And then in 2011, Camp et al. Constructed an extractor that ends up extracting from adversarial sources that say, okay, we require many more good sources, but since we have many more good sources, we can drop the entropy requirement to slightly sublinear n. And so kind of the first question is, can we kind of continue this trend and increase the number of good sources and as a reward, decrease the number of the entropy in those good sources, the entropy requirement in those good sources? So our first result does this. And so it says, even actually without increasing the number of good sources, we can drop the entropy requirement of the good sources all the way down to polylogarithmic in n. And then we show that we can actually also decrease the number of good sources down to roughly root n. And as a result, we also get better extractors for things called small space sources, which is kind of the motivating setting in this paper here. So our next result says, at the expense of introducing some small restriction, we can actually drop the number of good sources all the way down to subpolynomial in n. And this subpolynomial function is actually pretty small. It's roughly polylogarithmic in n. And then our final result says that if we increase the number of good sources back to what is required by Camp et al., we can still just require polylogarithmic entropy in the good sources, but now we can allow each bad source to depend on a polynomial number of the good sources. And so a super high-level overview of our framework that we use to construct these things is as follows. So first, we construct some some subroutine extractor for T independent sources with some extra property. Then we build some hypergraph where each hyperedge has size T. And then we apply the subroutine extractor over the hyperedges of the hypergraph in the following way. We take the XOR of the outputs of these subroutine extractors, and we show that as long as two special properties hold, this overall construction will output uniform bits from the adversarial source. And we show that if we want these two activation and fragile correlation properties to hold, all we have to do is construct a G with certain extremal properties and use a subroutine extractor that has some very strong conditioning properties. And we construct such a G using some recent advances in combinatorics, and we construct such subroutine extractors using some recent advances in extractor machinery. So that's kind of the high level overview of the proofs and constructions. And that concludes my talk. Thanks.
Thank you, Jesse. So we have a question by Shahadah Lovett. What is restriction free?
Yes, so so basically, we can occasionally we'll introduce some small restriction here. That is of the form big N should be relatively small compared to little n. So you have a few long sources instead of many short sources. And if you introduce this restriction, then you can greatly improve the number of good sources required, all the way down from root N to polylog. And this restriction comes from some restrictions on non-malleable extractors that we're using.
Okay, thank you. Other questions? So what is kind of the dream theorem you want to prove in this setting? Like, what are the best parameters you can hope for?
Yeah, it's a great question. So for the zero local setting, which kind of corresponds to the hidden independent source model, you can actually show that you can get just as good parameters as if the sources were not hidden at all. So you can effectively require just two good sources, and you could drop this entropy requirement to just logarithmic in n and have exponentially small error. And the best thing we have is kind of like this, so a root n requirement here. And for this kind of high locality setting, we can push this guy to 0.99 and this to 0.01. And so, yeah, so there's still a lot of room for improvement here.
I see. Okay, thank you. We have another question by David Zuckerman. If we had optimal non-malleable extractors, what result would you get?
Yeah, that's a great question. So, I think the main effect that would have would just be kind of lightening this restriction a little bit here. So this restriction is of the form big N is bounded above by little k to the 0.01. And you can, if we had better non-malleable two-source non-malleable extractors, this kind of restriction would be relaxed a little bit. But there's kind of a more general non-malleable extractor that we introduced in this paper that would allow us to handle much higher locality and kind of push this to 0.99 like I was discussing before.
Okay, thank you. Okay, yeah, okay, David says thanks. Yeah, I don't think we have more questions. Okay, thanks, Jesse.
Thanks.
Vedat, you can share a screen.
Is everything?
Yes, yeah, seems fine. Okay, our next talk is by Viraj Levy Alef. He will tell us about improved analysis of higher order random walks.
Thanks, Ankit. This is joint work with LabGLAO. So let me first start by talking about what higher order random walks are. The scenario that I care about is I'm given a collection omega containing k-elemented subsets of some finite grand set U. And I'm thinking K as some large number with respect to the cardinality N of the set U. And I want to be able to approximately sample from the uniform distribution of the set. And I'm just sticking to the uniform distribution for simplicity. And the way I want to do this is by using this following simple Markov chain, which starts from some set alpha 1 from omega, and obtains the set alpha t plus 1 from the set alpha t in the following way, by first sampling some element y from alpha t uniformly at random, and then removing y from alpha t, and then sampling alpha t plus 1 uniformly among all sets in omega containing alpha t without y. So you can convince yourself that the stationary distribution of this random walk is going to be the uniform distribution. So I expect that if I take sufficiently many steps of this random walk, I'm eventually going to, like the distribution of this random walk is eventually going to converge to the stationary distribution. So what I care about is the mixing time of this random walk. That is how many steps of this random walk I need to take such that this distribution of this random walk is sufficiently close to the uniform distribution. Okay, so let me now convince you that this definition is actually something natural by talking about the spanning tree exchange walk. So again, in the same setting I considered before, omega is now the collection of all spanning trees in a graph. The spanning tree exchange walk starts from an arbitrary spanning tree. And then what it does at every step is it first removes an edge of the tree uniformly at random, and then it completes the remaining set of edges to a spanning tree in a uniformly random way. Okay, this was well studied. This is an interesting case. So hopefully now we're convinced that this random walk model is actually useful for sampling combinatorial object, and it indeed captures many interesting examples of random walks, often studied for sampling purposes. And it also turns out to be important for agreement tests and some applications in coding theory. Okay, so what I want to do is I want to argue mixing, and there are many methods that you can use to argue mixing, like multi-commodity flows, coupling, log Sobolev inequalities, and etc., mostly etc. And in this work, I'm going to be adding a newish item to this list called local spectral expansion, which is newish in the sense that it was considered in the literature before, but it was the applications were very restrictive. So our contribution is making it more applicable. Okay, so what is this idea of local spectral expansion? So if you have a random walk matrix, a basic fact is that its largest singular value is 1. And the further the second singular value, the second largest singular value is from 1, the faster we converge to the stationary distribution. Now, you can use this ansatz to bound the mixing time, but if you care about higher order random walks, this gets quite unwieldy because the state space of the random walk is huge. So what we do is we use this approach of local spectral expansion. And the basic idea is that instead of looking at the state space of the random walk, which we care about, which is huge, we look at some local graphs and we show, oh, okay, all these local graphs expand, and therefore it must be the case that the higher order random walk expands too. So by expansion, I mean like spectral expansion. And the hope is that these local graphs are going to be tamer than the random walk itself. Okay, so as I told you before, this was considered in the literature before. The reason why there's an improved in the title of our paper is because we improved the previous works. So the previous works all have some regime where they can't give any non-trivial bound on the second eigenvalue, but we can always do this so long as some basic basic connectivity criterion is met. So I'm not going to explain what the result is. Instead, I'm going to just talk about some applications which might get you interested to read the paper maybe. So there's this folklore results that says if you have a graph G of maximum degree delta, you can notice higher order random walk to sample a independent set of cardinality n over 2 delta in polynomial time. The proof uses coupling arguments. I don't know any spectral arguments to do this. So one thing that follows from our work is that you can actually give a really simple spectral argument for this, for sampling independent sets of size n over delta plus eta, where eta is the magnitude of the least eigenvalue. And we always know, we know that this is always between 1 and delta, so it subsumes the well-known result. And it's really interesting because in the former case, I don't know how to do it spectrally, but in the latter case, there's a very simple argument. We can also do some similar things for sampling matchings or common independent sets of partition matroids. So whenever two partition matroids have a common independent set of rank R, we can use this higher order random walk machinery to efficiently sample a uniformly random independent set of rank R over 3. Also, we can also improve some result for the mixing of random walks, so mixing times of random walks in the complexes constructed by Liu, Mohanty, and Yang. Okay, so there is another application which is actually exciting. So the applications I told about were somewhat modest, but so one often considers spin systems and the statistical mechanic type applications, and one such system that one considers is the hardcore model. So the goal is sampling an independent set, and I assign each independent set weight t to the cardinality of that set. And this is a fundamental problem, and we knew how to solve the problem of estimating the partition function of this model by the work of Weitz. But it turns out by the work of Anari Liu and Ove Skaran that you can also solve the sampling problem using our method. And yeah, this subsumes the result of Weitz, albeit in a randomized fashion. And also this was recently extended by Chen Li and Vigoda to apply to all two spin models in the correlation decay regime up to uniqueness thresholds. Okay, so this was all that I wanted to speak about concerning our results. Now let me mention some open questions that I think are interesting before I conclude my talk. So we show a spectral gap inequality for higher order random walks. I think it's interesting whether you can do the same thing for modified log sublime inequalities, like whether you have like a local to global argument for log sublime inequalities. What are other examples of sampling problems where this like idea of looking to local graphs proves useful? And also, what are other random walks that we can use local spectral information to analyze? So like we look at this higher order random walk where, you know, it's somewhat restrictive, but it would be interesting if you can apply this method to other scenarios as well.
Okay. Thank you, Vedat. Questions? Okay, we have a question by Hengo. Do you think there is still room to improve your bound, or is there no lower bound?
So yes and no, in the sense that our result is tight for the complete complex. So like if this collection omega contains every k-elemented subset, then the eigenvalue bound we get is actually tight. But in our work, we assume, okay, like when we look at this local graphs, what we do is we assume an eigenvalue bound on every single one of them. And I'm not sure whether this is necessary. Like I think it should still be true that if you assume an eigenvalue bound on a majority of them, you should still be able to get a bound that is, you know, maybe improving our bound. But, you know, there are cases where our bound is already tight.
Okay, thank you. Okay, Hank says thanks. More questions? Okay, if not, let's thank Vedat. You can unshare your screen. Okay, Madhur has a, oh no. Madhur has a question. Yeah, Madhur, maybe
Hello?
you can speak. Yeah, we can hear you. Yeah.
Can you hear me?
Yeah.
Sorry, just wanted to ask, so this kind of sort of trickle down results that Vedat talked about, which kind of go from global to this sort of expansion of links. Do we know if they always require kind of the full downward closure, the simplicial complex structure, or can they also work with kind of the kind of structures Irith and Yotam use for agreement testing, which have some sort of downward properties, but not a full downward closure?
Like, what is it that you want to show? You want to show that this random walk mix is fast, or do you want to like prove something along Oppenheim's trickle down theorem?
Prove something around Oppenheim's trickle-down theorem, which when some of the things in kind of the middle layers in the simplicial complex are missing. Just you have some 3 or 4 layers that are needed for agreement testing, but not all k of them.
I think it's interesting. I can tell you out of the top of my mind, but I think it's a very interesting question.
Thanks. We can talk more on Slack.
Thank you. Okay, yeah, Vedat, you can unshare your screen. Aditi, you can share your screen.
Okay. Hi. So this is John Berkwood. Can you hear me?
Yes. Yeah. So our next speaker is Aditi Ladda, and she will tell us about strong self-concordance and sample.
Yeah. Hi. So this is joint work with Yen Tat Lee and Santosh Mampala. So in the setting of this talk is that we're given a polytope in n dimensions having m constraints, and the goal is to generate a sample that from a distribution that is nearly uniform on K. So this problem is fundamental problem, and it is also an ingredient for algorithms for volume computation, convex optimization, linear programming, etc. So the technique that that we are going to discuss is geometric random walks, which are Markov chains with whose state space is the polytope, and the stationary distribution, and we want these chains to have stationary distribution pi that is uniform over K. And the time requirement of these algorithms will be measured in terms of the mixing time of this Markov chain, where the mixing time to get the sample from a distribution that is epsilon close to the uniform distribution is given as the minimum time, such that after t the distribution, after taking t steps of the Markov chain, is less than epsilon close to the uniform distribution in total variation distance. So there are well-known algorithms to do this, and the most general walks are the ball walk and hit and run. So both of these, they work not only for polytopes, but also for any convex body, and then Dicken walk, which works specifically for polytope. However, there's certain drawbacks, which is the first two are not affine invariant. So they only assume oracle access to the convex body, but in case of polytope, we have something more. We have the explicit description of a polytope, so we can do better than that. And for the Dicken walk, the mixing time depends linearly on m, which can be exponential in n. So I'm just going to comprehensively describe our result here, which is we give a generalized version of the Dicken walk, and which mixes in order n square steps. Of course, there are some polylog factors in m. And now I'm going to describe the algorithm to achieve this, and also a general framework to analyze similar walks on polytopes. So this algorithm is called generalized Dicken walk, and for this, we're given a matrix function on the polytope, and with this matrix function, we define Dicken ellipsoids for every point x, which is just the ellipsoid centered at x, having the variance matrix hx and radius r. So using this, we'll define a random walk, which is for the current point x, from the ellipsoid centered at x, we select a point y uniformly at random, and then we go to y with the probability minimum of the rate of one and ratios of volumes of these ellipsoids. This is just the metropolis filter to make the stationary distribution uniform. So the standard Dicken walk also fits in this framework. For the standard Dicken walk, hx is the Hessian of this function phi x, which is called the log barrier, which is the sum of logs of the slacks at a point. So usually the function hx is the Hessian of a barrier function, but it does not necessarily have to be, just as long as it has certain properties to ensure fast mixing. So I think I'm just going to quickly describe these three properties. So to analyze the mixing rate, we define three properties for this function H to satisfy: convexity of log determinant, symmetry, and strong self-concordance. And our main result is that for a function H that satisfies mu symmetry, strong self-concordance, and has a convex log determinant, the generalized Dicken walk mixes in order n mu bar steps. I'm just going to describe what these properties are. Convexity is simply the log determinant of the Hessian is convex, and symmetry is that the ellipsoid with radius 1 is contained in this symmetric intersection, and the ellipsoid with radius square root of mu bar contains the symmetric intersection. I think a picture would make it more clear. So this is the symmetric intersection, and this is true for any point x in the polytope. And strong self-concordance is very closely related to a property called self-concordance, which is widely studied in the interior point literature. So self-concordance says that for any point x, the 2 norm of this quantity, hx to the power minus half, times the directional derivative at x in direction small h, times hx to the minus half, is bounded by the local norm of this vector h, where this h norm x is just the norm induced by this capital H function. So self-concordance enables a random walk to take large steps in the interior of the polytope. And also the log barrier is self-concordant. So now we want a stronger property to ensure order n square mixing, and that is strong self-concordance, which is simply, rather than bounding the 2 norm, we're bounding the Frobenius norm of this term in the in terms of hx. And this also translates to a nice, nice global property. I don't think I have time to go into that. So this strong self-concordance intuitively measures the rate of change of this barrier function in terms of Frobenius norm. So now this is the Ellis matrix, which is a function that satisfies all the three properties mentioned above. It's very closely related to the Ellis barrier, which was defined by Lee and Sitford in 2019. And so this Ellis matrix function, it is strongly self-concordant with convex log determinant, and its symmetry parameter mu bar is linear in n and has only log m terms. So using the previous theorem, it gives us a new result that the mixing rate of the Dicken walk with Ellis barrier is O tilde n square. And this is asymptotically the fastest Markov chain to uniformly sample a polytope. And so I think some open problems in this field are, do there exist barrier functions that mix in O n square steps, but also they are very fast to implement, that is just n and z a plus n square. And can we use this walks like these for faster volume computation? And also, what is the lower bound for such a Markov chain walk? It can be as low as O star n, so we don't really know. So that's it.
Yeah, thank you, Aditi. We have a question by J. Morris Rojas. For your generalized Dicken walk applied to a polytope, do you usually assume you have the linear equality description or access to the list of vertices?
We assume the linear inequality description.
Okay, thank you. We have another question by Holden Lee. Can you comment on why the mixing rate of gradient-based methods, for example, Langevin or Hamiltonian Monte Carlo, depends on M, while the weighted Dicken walk only depends on N? Can the techniques here be applied to gradient-based methods?
So here, the dependence on M was removed because of the design of a barrier function for which the symmetric parameter was not dependent on M. So I think we probably can do that, but it will again depend on designing like a barrier function for gradient based methods.
Okay, thank you. Let's take one more question. It's Morris again. Also, how nasty are the O constants in your more recent estimates? I remember pretty large constants in earlier work on hit and run.
So the constants are, there are some polylog M factors in it. So I think, yeah, the constants are like not very small. So I don't think we have an exact constant. There is still a constant plus a polylog factor, a polylog in M.
Mm-hmm. Okay. Thank you. Okay, Maurice says thanks, Square. Okay, thanks, Aditi. So this completes the session. Thanks to all the speakers for the wonderful talks and also the pre-recorded videos. So if people want to hang out with the speakers, you can raise your hand and then we will promote you to a panelist. Okay, Mother. Hi, Mother.
Hey, everyone. Shashank, just a reminder, you stopped recording, right?
Oh, right, sorry.
No, that's fine.